Hello everyone. So in the previous class we were studying about graph and we started with the problem statement of Koenigsberg city, Prussian city, and there was islands connected by bridges, and the overall idea was to traverse all the islands using the bridges and come to the same point. However, there is a condition that you do not have to use the same bridge again. That means only one time. So, in order to solve this problem, Euler was the person who came to know about this thing, and he decided to solve it how it can be done. He was the first person, like, who gave concept of graph. Okay, and then by using its techniques, he concluded something. And the conclusion of Euler was that there should be either zero or two vertices of odd degree. That's what he told. And there should be input and output from the nodes. Then only we can make a Euler walk. We can perform a Euler walk. And we can have a Eulerian circuit also. Circuit means from the point you start, you can come back to the same point. That is Eulerian circuit. Okay. Then we see applications of graph in data science, machine learning, and also directed graph, undirected graph. And here I am available with other types of graphs. You are seeing complete graph. So which graph is said to be a complete graph? Like, every node is connected to every other node. Such graph are complete. So we are having a figure where there are 12 nodes, and each of which are having an edge connecting to every other vertex. So if in a graph there are n vertices, which is denoted by kn, they are exactly n choose two edges. What does it mean? N choose two edges like this. To be very simple, you have to connect every vertex to vertex by an edge. That means ultimately you have to create a mesh. We do study topology and networking, and mesh topology is something where we do connect every node to every other node. You can see, if I am having two vertex, this is how connect, three, this is how connect, every to every connection. You can see k2, k3, k4, k5, k6, k7. That's what they are saying, kn. Okay, so we are having n vertices, so represent the graph by kn. There are exactly n. We can choose two edges. What does it mean? There are exactly n. Choose two edges. Okay, might be somewhat confusing, but the point should be clear. Like in this way, connect every to every. This is a complete graph. Okay, and then complete graph arise in the number of settings, and often useful in understanding more complex problems, because here ultimately now with one node to another node you're trying to identify the relationship. If we are having multiple relationship between the nodes, that's what we do in neural network also. We connect every neuron of one layer to every other neuron of another layer. That's what we do. For example, if there are two neurons here in layer number 1, there are two neurons in layer number 2, we connect this neuron to this also, we connect this neuron to this also. Here also the same thing happens, every to every connection. So same thing in complete graph, every to every connection. Relationship only we are trying to identify. From that only, one more category of graph came, bipartite. Okay, bipartite graph. Bipartite means it is. I think from the name itself it is clear. Bipart. That means you have to divide the graph into two parts. That is bipartite. Two parts. Break it into two parts. So we are having two sets actually. Size of m and n. For example, that will make what is m and what is n. That is a bipartite graph. Okay, so a graph is bipartite if there exists two vertices in the same set that are joined in an edge. That means if any vertex in one set is connected by an edge to every vertex of the opposite set, then it is said to be complete bipartite graphs. Understand what it is trying to say. A graph is bipartite if there exist at least two vertices in the same set that are joined by an edge. Okay, what does it mean? What it means now? Understand from here. This is bipartite graph. How? Let me divide it. This is part one. This is part two, or I would say that this is set one, and this is set two. In set 1 I am having these two nodes. In set 2 I am having these three nodes, and according to the definition every node here is connected to every other node of another. That means every node in set 1 is connected to every other node in set 2, but not like among each. Okay, from the same sets, no. Okay, that means I am not connecting yellow to yellow. No, that is not happening. Neither blue to blue. Okay. No, I am not connecting them. You are having two set 1 and set 2. So the nodes which are present in set 1 and the nodes present in set 2, they should be connected. Okay. So every to every from this. This is bipartite. Okay. So ultimately they are used in like matching problems. We can think of each of the two set. Okay, we are having obviously two set, two group. Okay, so I'm trying to match. Okay. So a classic example of bipartite is interested in dating the people who only present in the another group, not the same group. Okay, so just make the group and connect one to one. And if everything is connected, now every to every it's connected, then it is complete bipartite. This is complete bipartite. No? If every to every is connected, one set to another set, complete bipartite. We are having one more category. So complete graph, bipartite graph, planar graph. Planar, plane. So planar graph is any graph that can draw on a flat piece of a paper without crossing. This line is important. Without crossing edges. See, edges should not cut. If you are making a graph, edges should not cut each other. It should not be like this. Intersection is not supported here. Okay, so in graph number one, you can see here. This is not planar. Why? Because you can see intersection of the edges here. Intersection. This is not planar. If you want to make it planar, you do one thing. If you want to connect an edge between these two nodes, these two vertices, just round up. Do this thing. This is planar. This is planar. And this one also. This is also planar. There is no intersection of the edges. Okay. So such kind of graphs are called as planar graph. Right. So yes, hmm, it is not immediately apparent that the graphs on the left and the right have the same structure. Okay, fine, yeah, that is also one of the question. Because okay, if you do talk about this and this, these two graphs, what does it represent? It shows that they are this having the same structure of vertices and the edges. See, same number of vertices are there, same number of edges are there, but there is one shift you did. Following a shift from left to right of the graph, what you did is you want to make it a planar. So in that particular case, in order to avoid the intersection, you change the path of flow. So it came under the category of planar. One didn't follow this rule. Okay, and such kind of problem, this problem of identify which graph is similar, we do have another kind of graph. They are called as isomorphic. Okay, so there might be a question. Okay, one is planar, one is not planar, but are they similar? There might be a question. These two graphs are similar graph or not? Okay, they are not. One is planar, one is not planar, but are they similar to each other? So similarity, okay, every, we are having four vertices here also, we are having four vertices here also, we are having the same number of edges, and also they are connecting to the same nodes. Obviously they do share similarity, but see the structure, there is a change in the structure. Okay, so the change in the structure, that reason, okay, one is converted into planar, another is not planar. Okay, so there is one more term that you should be knowing, that's isomorphic graphs, to identify that they are similar or not. So similar structure in the sense that it's talking about related to the vertices, it's talking about the number of edges, it's talking about that with which vertex to which vertex are edges connected. So it is isomorphic, but you can see that one is planar, one is not planar. That's the difference. Okay, here also, if you see, again, four vertices are there. Okay, but there's a difference between these two and this one also. In this vertex, you are connecting three edges. Okay, so they are having different structure. Okay, fine. Now, there is a theorem, Wagner's theorem. That means a graph G is planar if and only if the complete graph K5 means 5 nodes, of a complete bipartite K33 can't be obtained from graph G by deleting an edge or vertex connecting them, contacting them. That means a graph G is planar if and only if there is a complete graph. If it is a complete graph, okay, complete means every vertex is connected to every other vertex. That is a complete graph. Bipartite, okay, that means if the complete graph K5 on the complete bipartite graph K33 can't be obtained if a can't be obtained from G by deleting an edge or vertices. If you delete any edge or if you delete any vertices. So see, this is K5. That means 5 vertices should have to be there. So in 5 vertices, we are making K33. Here you can understand. This is K33. Why K33? Bipartite hai. Okay, convert this thing into like in this way. K33. ये तो आपका K5 है. This is complete graph because we are having 5 vertices and every vertex is connect to every other vertex. So this is complete. And this is K33. That means I do have a set of these three vertices. I do have a set of these three vertices. So K33 means this is set 1 and this is set 2. I am having two sets. And this is biparted. Complete biparted. Okay. So it says that contracting vertices is what happens when an edge is deleted from the graph. And the two nodes at the end of the edge are joined. Two nodes at the end of the join are joined. Okay, so this theorem is a very powerful idea and important to understand in terms of your what? In terms of relate what you are trying to relate here. Relating to graph which is planar or not. So what do you think? Is this graph planar or not? Not at all planar. This is not edges are intersecting. This is not planar. This is also not planar. Both of them are not at all planar. So what Wegener theorem is trying to show you, it's saying that a graph G is planar if and only if the complete graph K5 on the complete bipartite graph K33 can't be obtained from this graph. See, if the graph is planar, neither I can't obtain this thing from a planar graph. Graph is planar if and only if the complete graph K5 and bipartite can't be obtained. I can't obtain this thing. I can't obtain this thing also. If there is a graph which is planar, I can't obtain this and this both. Why? Because they are having intersection edges. And planar says that okay, there should not be any intersection. So this is also having intersecting, and if you try to just change the orientation, that means okay, if you try that okay, इसको इधर से connect कर दो, ओके इसको एंड जस्ट लाइक इसको भी कोशिश करो इधर से कनेक्ट कर दो लाइक दिस ओके इफ यू ट्राई समथिंग फ्रॉम योर साइड टू चेंज द कनेक्शन यदि आप इफ इट इज पॉसिबल करके देखें ओके ये तो बिल्कुल भी नहीं हो पाएगा K33 there is no chance that K33 can be converted into planar anyhow if you just try to change the orientation it will it will show the intersection okay so एवरी टू एवरी कनेक्शन है इंटरसेक्शन है ये प्लेनार नहीं है दे आर नॉट प्लेनार दैट्स व्हाट वेगनर सेज वैगनर्स रूल ओके फाइन हाँ हियर इज द रिलेशनशिप दैट्स व्हाट वी यूज इन द ग्राफ थ्योरी that means someone is selecting cap he is selecting shirt also and he is selecting trousers also this color so if there is every to every relationship that means any kind of combination is possible from here any kind of combination is possible okay so choosing a dress combination that's what we can say relationship we are using in the graph theory okay so if you choose each item from each category one cap another t-shirt and so on you can see that direct all these combinations are mentioned okay by nodes and the edges fine this is also one of the example of graph theory social network okay there is no other sense of describing a social network only graph can explain this is the only means okay fine because else the things get complicated ये graph you're you're making the nodes you're connecting via edges social network okay fine so the type of graphs I have already explained to you undirected graph you know where I don't have any direction so this is undirected graph directed graph also I told you When I do have a direction, this is directed graph. Okay, and the direction, like for example 3 to 2, so it will be written like this: 3 to 2. I can't write 3 to 2 like 2 to 3. No, this is wrong, because you can't go from 2 to 3. There is no edge directing towards 2 to 3. This is wrong. Whatever be the order, just mention it. Okay, fine. Okay, weighted graph. These are the weighted graph. And by seeing the weighted graph, I hope you remember the problem of shortest path algorithm. So shortest path algorithms are based upon weighted graph only in computer science. Engineering, we do solve this question. We say that, okay, this is the source, this is the destination, kindly find the minimum path to reach from source to destination. So there are many algorithms who do perform this thing. So these are the weights. Okay, we can assign weights to the edges. Okay, it can be anything according to your problem statement. We can do that. Okay, weights to the edges. This is weighted graph, and very important. I just told you, very important phenomena, because we use this technique in finding the shortest path. And there are many algorithms like Prim's algorithm, Varsha's algorithm, Floyd algorithm. Many algorithms have been taught, in which the favorite one was mine was Prim's. That was easy. And also minimum cost. There is one more algorithm in ADA, that is minimum cost. Okay, so we can see such kind of algorithms related to the graph. Okay, so weighted graph, there is one thing. Weighted graph can be directed also and undirected also. There is no issue. It can be directed and undirected. Okay, the one which is in the example, that's what we are seeing, that is undirected. Okay, there is no direction here. Okay, so it defines the cost or the distance of the node from one to another. Okay, so we could represent this relationship in a form of a triplet UVW. That means, so this is also node, this is also node, and this is the weight between them. Okay, which shows this thing from where the edge is coming, from where it is going, and what is the weight. Okay, fine. So if you want to travel between the cities from green to orange, you have to pay $3. Okay, so or either you have to drive 3 miles. So whatever that weight represents, it's up to you. Your problem statement. Okay, so you can define there. All right, so it's very simple. Next one is tree. That is a special kind of graph. And tree, obviously, we are having one algorithm, that is a decision tree in our machine learning. Okay, so tree is a special graph. Why it is so special? Because I already told it does not having loop. Does not have loop. It never close. Tree never close. No circuit. No circuit. That is why it is a tree. That means if there are n nodes, there will be n minus 1 edges. We should not have n nodes and n edges. No, this will close the tree. Okay, so according to the property of trees, it is it is undirected graph with no cycle. Okay, so n nodes, n minus 1 edges, undirected graph with no cycles, and this is the nodes and the edges numbers. Okay, like, okay, this is tree. Okay, this is tree. Obviously, we use this concept only. We can say that this is also been like a tree only. According to my definition, it's also following the rule tree. Okay, so all the graphs given above are tree. Even the leftmost one, because it has no cycle, it is a tree. But you are seeing that, sir, tree should have like this. So according to your computer science concept, this is like a tree, but we can't deny this thing also. This is also tree. No circuit, tree. This is also no circuit, tree. But in general, we use this such kind of cases like binary tree, something like that. Rooted tree. A rooted tree is a tree with a designated root where all the nodes are either coming towards the root or going away from the root. This is a rooted tree. See, and any of the node can be rooted, either directed towards it or either away from it. This is rooted. Obviously, we say a root of a tree. While solving a problem in decision tree, also I will say root of the tree. So tree starts on the root. In real life, this is the tree. Okay, so this is the root. In computer science, we go like this way. Order change मतलब उल्टा है ये. This is like, okay, opposite. And this is what we make tree. Okay, this is also like rooted tree, either coming in or either coming out. Okay, so the leftmost tree where it is coming towards the root, it is in tree, else it is out tree. So in tree and out tree. Okay, then directed acyclic graph, DAX. That means directed graph with no cycle. Acyclic means, what does it mean by acyclic? Acyclic means no cycle. That they are called as DAX. So these graphs plays an important role in representing structure with dependencies as schedulers or compiler. Yes, in operating system now. In operating system, we can use these concepts. A directed graph, DAGs are the directed graph with no cycle. Now you will be questioning, sir, cycle, sir, ये close लग रहा है sir. ये तो close लग रहा है. Here you can see, sir. You are telling ना कि there should not be any closed, so that will be tree. But ये tree नहीं, ये graph है. मतलब tree is also part of a graph without cycle, and it is also saying that we don't have a cycle. तो ये तो tree होना चाहिए. Cycle नहीं है. If there is no cycle, then it should be a tree. But sir, यदि आप you are saying that this is also dag. Why? We can say we can see the closeness here ना. तो सर इसको क्यों बोल रहे हो आप डैग? Why? And you are talking about schedulers and the compilers. Okay, let me share my entire screen now. If you talk about scheduler and the compiler, how the operating system related to the process it works. Scheduler and the compiler. Just wait. You are having different types of processes. Okay, in operating system we do have that. Like this is the start, and that means this is the there are different process states, and we make a process state diagram. So this is the starting state. Then your process can come in running state. This is okay, process start हुआ, ये run हो रहा है, and then it can terminate. This is ending state. However, meanwhile, during running, you may halt also. You may halt also, and then it will again go back to the initial state. This is the initial state, and then again it can come under execution. Or either if you have halted, you can forcefully terminate it also. So there are different states of a process. We do make this in a process state diagram in operating system. Now we study this concept, process state diagram, and they are DAGs like. They are like DAGs, directed acyclic graph. Hope there should not be any cycle. However, what I see here is okay. This is creating like a cycle structure. We are going to avoid this thing, such cycle structure. Let's see what happens, what it is trying to define. So we can use this graph to show topological order between something meaningful. For example, if you use DAGs in a process manager, that's what I was telling, no? Processes. Okay, so it should be completed before proceeding Z. Process X and Y should be completed before processing. Okay, process manager, whatever. I just focus upon the type of a graph. So no cycle. See, it is going here and here, and it is going directly. How you say that this is tag? I do have a doubt here, which I made. This one, this kind of direction. Idhar aaya, then it came here, and then it came here. Isn't it a cycle? This is a cycle. But what's in that particular case, which is shown in the diagram? It came here, it here, and it came here. No cycle is created. That means a repeat nahi ho raha. Cycle is not created. That is why it came under a category of DAG. Directed. This is directed. Directed means there is a direction. Acyclic. Okay, so directions are not creating a cycle. Okay, so this could be a cycle. This is cycle. It's not a cycle. Here, here, but I can't go back. If I could go back, then this is a cycle. But this is also directed towards node only, not cycle. A cycle, acyclic. Sorry, that's what we can say. Okay, so nowhere I'm getting such kind of here also. This, and this. Okay, fine. Bipartite graph I already explained. Okay, that means you are. These are also bipartite graph. Okay, that means you are dividing the entire graph into two parts. This is one set. This is another set. So you might have a question, sir. Is it mandatory that every time every node is connected to every other node? No, it's not mandatory. This is bipartite. This is set 1, this is set 2. It's not mandatory that every node should be connected to every other node. If it is connected, then it is complete. Complete bipartite. So this is bipartite. I am having two set. There are some nodes connected from here to here according to the relationship. Okay, according to the relationship. But it's not mandatory every to every. If it is connected every to every, then like fine, complete bipartite. So this is complete bipartite. And what you say about this thing? What you say about this thing? This red is connected to this, and this red is connected to this. Red to red are not connected. Remember, red to red are not connected. If red to red connected, that means they are part of same set. How I can connect? So they are not bipartite. This is also bipartite. Okay, all these are bipartite. This is bipartite. Okay, because red is connected to black. Okay, fine. Complete graph I already told. Every to every connection, this is complete. This is complete graph. The same diagrams I have shown. Okay, complete graph are considered as a worst case graph. Why it is considered as a worst case? Because every to every connection na complicated हो गया ये. This is very complicated. Up till certain number of vertices we can take, but if the number of vertices are increased, na, that will if you are going to connect every to every, that will be like okay, so much. Okay, there will be so much vertices. So it's a worst case graph. How to represent a graph? These are the ways to represent a graph. For example, you are available with a graph. I need to transform it into some matrix. That's what we do in finding the shortest distance. We transform them into a matrix because matrix will give you a solution. Graph is a representation. For solving, you have to convert it into matrix. So this is one of the simplest one. Adjacency matrix. This is very simple. Take all the nodes on the row and like this. Okay, fine. Rows and columns. Just consider all the vertices, and this is directed given. So A to B 4. So from A to B 4. A to C 3. So A to C 3. Nothing else. Then B, okay, there is nothing outgoing from B. All are 0. C, in C to D 2 is there. Okay, only 2. Rest all are 0. So if there is outgoing, then only fill. Ingoing के लिए नहीं fill करना. Only for outgoing. Okay, this is adjacency matrix. This is directed. If you don't have any directed, we are available with the weight, so fill everything. But at this current the diagram, we are having the weighted directed graph. Directed graph that's having weights. So just outgoing now we are filling and converting it into a matrix. And after converting into matrix, we can solve it. Okay, so it can be used as a purpose of shortest path. Okay, so just like that matrix, we are having adjacency list also. Okay, another important data structure which is having the graphical to list representation. Okay, so here it is. I am having 5 vertices. Okay, these are 5 vertices, and I do have the weights also available. So what I did, I wrote all the 5 in this way. I just prepared like list of 5. So from 1 to 2, 9.3. Okay, 1 to 2, 9.3, and 1 to 5, 3.6. Okay, so just made it 2, 9.3, 5, 3.6. And what is list now? Very important data structure, list. And list always created trouble for me also when I do study the data structure. Why? Because in list we are having two field. One is the value field, one is the pointer. Two fields are there in a list, value and the pointer. So pointer points, when I also study at my college time, now this like list representation and making a code on list, very hectic, because it has a topic called as pointer, and what we study there in the pointers are the variables which store the memory address of another variable. That's what we have studied. Okay, they behave as like na, like a reference to another variable. Okay, we can point to the memory address of another variable with pointers. Okay, so it is referring. Okay, it is referring. Fine. So here, if I need to represent this graph in form of a list, then obviously it's hectic. You can see that. Okay, for one, I made 2 and 5. For 2, you are having 1 also, you are having 3 also, you are having 4 also, you are having 5 also. 1, 3, 4, and 5, all you are having. For 3, you are having 2 also and 4 also, 2 also, 4 also. But anyhow you have to adjust the pointers. For 4, you are having 2 also, 3 also, 5 also. Okay, so 2, 3, and 5. Anyhow, you have to adjust the pointers. from where to where it is connecting. So all these are like preparing list from the graph is like, however, preparing matrix is very easy. Just write it down in this way and put the weights inside the matrix. But making a list is complicated. Okay, fine. We are having edge list. Edge list is easy. No issue with the edge list. Okay, it is very easy. Like A to B, 2, B to C, 8, C to E, 1, and so on. Like this is edge list. Okay, this is easy. But like this one, adjacency list preparing from a graph is complicated. Like we have to set the pointers. Okay, so what we have seen in the graph theory is the entire concept relies on relationship. Okay, you are available with a node, you are available with another node, and you are having an edge between them. That means you are trying to show some relationship between node A to node B. In that regards, there could be many kind of relationships. So by different types of graphs, you are trying to show relationships only. Whether you say initially complete graph, every to every related. Bipartite graph, that means set 1 and set 2 relationship. How set 1 is related to set 2 relationship again. There could be complete bipartite graph also. Okay, you are having directed, you are having undirected also graph, weighted graph also, you are having unweighted, you are also having. You are having directed acyclic graph where you don't have any cycles. Okay, you use such kind of concept in operating system to show process scheduling, compiler scheduling, all those things. Okay, and then like just recently we studied that how to represent a graph in form of matrix, in form of list. This is the easiest case, matrix representation to find the shortest distance. Okay, shortest distance. And we are using the concept of graph in our data science for many reasons. Okay, because we do have architecture. So architecture, obviously I need to make a graph for the architecture. Okay, in deep learning, obviously how nodes are connected, how your yes, nodes are connected to other in the layers. Also, decision tree in machine learning, you are building a tree, it's a graph only. Okay, and I hope you heard about this concept, graph neural network also. Not a new concept, but not so much famous, but it's coming. Okay, graph neural network. So just to show the relationship, graph key is very much important. Rest, the thing is, once you have a relationship, once you have a values, just turn it into matrix to solve. Matrix is game changer. Okay, if you can represent something in a matrix, it's a game changing thing. Okay, that's what you can do. This is about graph. Not more than I'm going to talk about the graph. Just I want to have an introduction, different types of graphs. Rest you are going to see in the applications. Okay, fine. So it ends with the concept of graph, and next will be calculus. Okay, where we are going to talk about the differentiation, because that is mostly used in the calculus in data science and machine learning. Integration is also used but less. Differentiation is used more. Okay, differentiation is used more because we have to del by del. Okay, this is used to identify the slope and also for optimization. Okay, so differentiation is used more. All right, fine. So in the next class we are going to talk about the calculus. There will be discussing about minima, maxima. Okay, such kind of terms important. Okay, and then after, I guess, not so much time I will take. Then the next one will be, we are going to head towards linear regression, our first algorithm for machine learning. Just only calculus is remaining. Then I will switch to the linear regression. Okay, fine. Specific projects platform to for us to knowledge graphs directed. Okay, if you talk about platforms for graph, sir, as I already told, that means the subjects which we do study, like discrete mathematics,